Hello, I'm Silky Park. I'm a PhD student at the Department of Electrical and Computer Engineering from Seoul National University, Korea. Now I'll present our work, Influence Balance Laws for Imbalanced Visual Classification. Many real-world data often exhibit long-tail distribution. The model trained on such imbalanced data tends to overfit the majority classes. Therefore, imbalanced visual classification aims to make a robust model while training on the imbalanced dataset. Previous methods can be divided into three approaches. Data level approach directly balances the training data distributions by resampling or generating synthetic samples. However, undersampling can lose some valuable information, and oversampling can make the model to overfit to repetitive samples. Recently, meta-learning methods have shown promising results, but these methods are difficult to implement in practice. Lastly, reweighting approach assigns different weights to each sample according to its importance. Previous methods have focused on class-level distribution. However, not all samples in a dataset play an equal role in determining the model parameters. That is, some samples have greater influences on forming a decision boundary. Therefore, we argue that each sample needs to be reweighted differently according to its impact on the model. Therefore, we come up with the following motivation question. How can we appropriately reweight the importance of each sample while preventing the model from overfitting to majority classes? Vocalists tackled this problem by assigning more weights to hard examples. But we discovered that, as training progresses, most hard examples belong to majority classes due to the high capacity of deep neural networks. So, to prevent overfitting, we aim to reweight samples according to their direct influences on making the model. To measure the influence of a sample, we focus on the influence function from robust statistics. As shown in the figure A, we observe that the influence of the majority class is much greater than the minor class in the imbalanced data. This shows that the influence of data can be a meaningful clue. From this, we propose a new loss function that downweights influential samples causing overfitting. To present the proposed method, let me recap the influence function first. By definition, we can measure the influence of a point x on model parameters as equation 1. From this, we derive the IB loss. First, we define the influence balance weighting factor as equation 2. For the details and the rationale, please refer to our full manuscript. When using the softmax cross entropy loss, IB weighting factor can be further simplified as equation 3. We reweight samples inversely to the IB weighting factor as equation 4. Finally, we add a class-wise reweighting term lambda k to the IB loss. This class-wise reweighting can further control the influences depending on the classes. Lastly, the influence balance training process comprises two phases: normal training and fine-tuning for balance. Let's now move on to experimental results. We used the most frequently used benchmark datasets in literature. Here, imbalance factor is the ratio between the most frequent class and the least frequent class. We compared our method with the representative cost-sensitive loss methods. This is the comparison of classification accuracy on benchmark datasets with various imbalance factors. As you can see, our method outperforms recent methods in all cases. Furthermore, the class-wise accuracy shows that the significant improvement has resulted from the minority classes. In conclusion, let me sum up our main points. Thank you for watching the video.